Today, I'm going to teach you the Floydd warshal algorithm. First, let's review its place among the other shortest path algorithms. Previously, we learned that Dijkstra's provides the shortest path from one node to all nodes. Bellman-Ford is similar, except negative edges are allowed. Floydd warshal is different in that it discovers the shortest path between all pairs of vertices. Of course, negative cycles are not allowed in any of these algorithms. We'll start with the pseudocode, but don't be overwhelmed. We're going to walk through it step by step. First, we need a graph. We'll use the one on the right with 4 vertices. We create a distance array that keeps track of the shortest path between nodes. For example, row 3, column 4 will store the shortest path from node 3 to node 4. Let's initialize each node's path to itself to 0. Our next step is to loop through the edges of our graph and fill in the table with the corresponding weight. We'll start with edge 1, 3, which has a weight of -2, and add its value to our table. We loop through the remaining edges, adding their weights. We're ready for the meat of the algorithm, the nested for loop. I'll hide most of the pseudocode as our main concern is the if condition and the 3 counter variables, I, J, and K. We start with them all equaling 1. Let's fill in the corresponding values from our table. As you can see, the if condition isn't met, so we don't update our table. Setting J to 2, we see the same result. Likewise, when J is 3 and 4, our if condition isn't true, and we don't make an update to the table. This can be tedious, so let's skip ahead to an interesting iteration, with K still 1, I equal to 2, and J equal to 3. Plugging in the values, we see that this time our if condition is met. Therefore, we update the path from 2 to 3 with a smaller weight, which is 2. Again, let's skip ahead to an interesting iteration. This time with K equal to 2, I equal to 4, and J equal to 1. We found a new shortest path from 4 to 1 with a weight of 3, so we update our table. By now I'm sure you see the pattern and flow of the nested for loop. I'll show you the rest of the algorithm without voiceover, and I'll skip the iterations that have no effect on our table. This is the last iteration that affects our table. Here's our result, a table of shortest paths between all pairs of vertices. The time complexity of this algorithm is big O of v cubed, where v is the number of vertices. Because of this, I can't see anyone asking you to do this by hand, but hopefully this video improves your understanding of the algorithm and your ability to code it. As always, thanks for watching. There's a lot more coming, so please comment your suggestions below.